Okay, so good afternoon and welcome to this quick tutorial. What I want to do here is to do a bit of a uh, hands-on handholding to go from a blank project all the way to getting blinking an LED on this TiVA board. So what you see on my screen here is this folder that contains all the documents that you need. The first is of course the technical reference manual, that's the TRM for the Cortex M4. The next thing that you need is the generic device user guide, so that's the usual. And then this one is the user guide for the assembly language tools. This is not needed right now, but we'll use it later on when we uh, look into more details of how the compiler converts code into assembly. And then we have this is the data sheet. So this is the data sheet of our microcontroller itself. And then the final thing we have is the schematic for the board. So this is the board schematic. These are the main PDF documents that you should have with you in order to be able to do most of these experiments. So let's get going. The first thing you need to do is you need to start CCS. So as I start CCS, the first thing that comes up is this. And I don't even want to use this existing workspace. So what I'm going to do is I'm going to go and change this to something else. So what I want to do is I want to go to a different directory, this one, and this is what I want to use as my workspace. So I launch. And the only reason to do that is, of course, I will not get all my old projects and all. I really truly want to start from scratch. So let's see how that works. So this is my Code Composer Studio, that's CCS, that is now started up. Now the first thing we want to do is start a new project. So go here, new CCS project, and now here I'm going to set my device, which is 4C123G G6H GH6PM. So that's the device I want, and the connection that I want is this Solaris in circuit debugger. The project name, let's call it Blink. And you can see I have two options. I have the option of using the CI compiler, or I could use GNU compiler, which is GCC. Now, like I said, it's probably not a good idea to switch halfway through. So you stick with whatever compiler you are going to use and don't change it. So this is fine. We want the executable to be generated. All this is fine. Device Indian is listed. Linker command file, it should pick automatically, and everything else should be good. So we say finish, and that should give us a nice blank project. So here's our nice blank project. Just to do a bit of a sanity check and make sure that everything is good. We can do a clean and then say build project. So there you go. The build is complete, and what you see down here, this is called the console window. So the console tells us what we did and what are the results. So build is what happened here, and you can see that yesterday in class I talked about the command line, right? So this is the command that is called, and then these are the options that are passed to it. Then it builds this file main.c, and it invokes the ARM compiler, and then this is how the ARM compiler is invoked. So this is the command, and these are the options. You can see all the options here, and then it has completed, so it's successfully finished building main.c. Then in addition to this main.c, we also have another C file which is called startup_ccs.c. So our build system goes and builds that as well, and then it succeeds, so it says finished building. Then yesterday I talked about how multiple C files are converted into a single executable, right? So after this building is done, then we need to build the final target, that is the .out file. And so therefore it calls the ARM linker. And then when it calls the linker, you can see there should be a main.obj and the startup.obj, right? So the two C files got converted into .object files, and then at the end of that, it has produced our final executable file, which is blink.out. Okay, so this is the basic build process. We have really not done anything at this point. We have just added an empty project and just checked that we are able to build it, everything works, and we've got it. Successfully building. So now, of course, in our embedded system, normally we don't want the code to return because there's nothing to return to. So let's write int x, and then of course we don't want to write int. We want to invoke the standard library, right? So we want a 32-bit int, and for that the data type is uint 32_t. Okay, and uint32t is not defined anywhere yet, which is why it looks green here. So to do that, we have to invoke, or we have to include stdint.h. So now let's try doing something here. Let's say while 1 x plus, just so that we don't ever break out of this loop, and then we'll see what's going on. So now let's go and build this again. So now build project. So normally it's okay to just say build or rebuild, but sometimes if there are some strange things happen, you may want to just do a clean, which basically deletes all the built files. You can see here, right? So rm means delete. So just all the output files and all the object files, all of these basically get deleted in this clean process. So sometimes you may want to do a clean before you do build again. So there we go. So now we've got the build has successfully completed. So finished building, everything is done. But we got a little warning here, which says variable x is used before its value is set. So you can notice that we have not set a value to x, but we have incremented. We have used it without actually initializing it. So let's fix that and assign it an initial value of 0. Let's initialize it and let's go build this again. So build project. And if I remember correctly, I think the shortcut key to build is Control B. So let's build all. But of course, right now there's only one project, so no problem. We can use Control B to build our project. So now everything is done. Our warnings are gone. But of course, TCS knows that we are trying to do something, and then it gives us some suggestions to optimize our program better. So for now we are going to ignore that and just go on with whatever we are doing. So you can see that the problems have now disappeared. We don't have any errors, no warnings, and you can also see that this memory allocation, you can see what has gone where. So we talked a little bit about this. We have not talked about it yet, and all of these things are given to you just in case you need them later. So now we were able to build. Now let's try and actually program this. So you go debug, and the icon for that is up here. So let's say debug, and I think the first time it takes a while for the first launch, but once that is done, we should be able to. There we go. So now we've got this, our debug interface, and we can click on this to step into the code, which is basically to run this code step by step. So you can see first initialization, you can see the value is some garbage value, which we don't know what it was. So next step, you can see it got assigned the value 0, it got initialized to 0, and then this loop is going to run continuously and then give you increments of value x. So you can see in the next time I click on this step into, the value becomes 1, then it becomes 2, then it becomes 3, and so on and so forth. Okay. So now this is C code, but actually your processor or your microcontroller is not executing C code, it's executing assembly. Just to see that, we go to view and we go to disassembly. So what it shows you here is for each function, let's say this is function main, right? So where is this function? This is at the default, this is at the location 298. So if you just scroll up, we'll see that at 298, indeed our function main exists. So you can see at address 298, yes, we can see that main exists. So what is the first instruction that we have given it? This x variable, that is a 32-bit int, unsigned 32-bit int. This is assigned the value 0. Okay, so you can see that the equivalent instruction is to move 0 into register R0 and then move that value into the RAM, which is the stack space. Then we are running a loop which is x++. So now to step through this, what we need to do is we need to do assembly step into. So we want to step by step execute assembly rather than execute C step by step. So for that we can do this, which is assembly step into. So when we do assembly step into, this is what happens. So we do a step, and you can see that on this side our program increments one by one, right? So what is happening here? This is our while loop. Okay, this is the while loop. And what does the while loop do? Basically, it just says go and run this code again and again. And what is this code? This is your x increment. So let's see how that x increment is happening. So x needs to be incremented. So basically, you load the value of that variable into register R0. So let's watch our registers also. In fact, we can split this view and watch the variable x. Let's move this over here. Variable x, and let's watch our variable. So let's say we want to see R0, core register R0. So you can see its value is currently 5 because we are going to now load this value in. Okay, so this value got loaded in. We are going to increment it by 1, which means now it became 6, but our variable is still 5 because we have not written it back into memory where the variable is stored. So then we store it back. That was your str, and that's when the memory location got updated. That's where the variable got updated. What is the next instruction? The next instruction is branch to this L1 loop 1 pointer, which is up here. So the next step, processor jumps back here, again loads it from memory, does this, and it keeps going on and on and on like this, right? So this is a very, very simple program that basically runs a while loop in which we are incrementing a counter. That's all. Very, very simple program. Now, few things of note here. One is, of course, where is this program stored? Okay, so you can see that this program, where is it running? It is running in memory location that is 0000002A0. Okay, so what does that tell us? It tells us that this code is executing from flash. Okay, so these instructions, these opcodes, or the executable itself is stored in the flash, and it is running from flash. Okay. Next thing I need to know is where is this x stored? Where is this variable x stored? Okay. So to do that also we can find out here. So let me just put this back here. Let's go back to variable, and you can see location. Its location is stored here. Okay. So there's another way to check this, and that is where is this load happening, right? So we are loading this value from an address that is stored in R13. So let's go to R13 and just quickly check what that address is. So you'll see that that is hex 2000-01F8. Okay, and you'll see that that is indeed the address of our variable x. Sorry, was it not matching? 1F8, and this is also 1F8, correct. So that is where our variable x is stored. Now the question is, what kind of memory is this in here? So we know that this is SRAM, right? So we know that this is SRAM, which is inside the processor again, and that is read-write. It is readable as well as writable. Obviously, that is why we are able to read from X and we are able to write to X as well. Okay, so that is this very simple program. And next thing we are going to do, we will start trying to experiment with modifications of this program and see what happens.